Okay, after the introduction movie, we're going to look at the movement of charges. Let's start with a little experiment. You see me here rubbing a plastic or a PVC tube and touching some strange objects. What is this object? Let's put it on pause for a while. You see here perspex just with an indication, but the main part here, this is metallic. This is metal, and you have a little rotatable stick here, which is also metal. So this is metal connected to this rotatable piece. Well, I touched it with the negative tube, and the piece opens. The stick opens. So let's continue. You see it opens, it stays open. And now I use a glass rod, and I rub it again. And after a while of rubbing, I touch that, and it closes. How can that be? Well, let's look at it. We've got here the electroscope, and the electroscope has a metal piece, and here a rotation point, and also a metal stick. And when I go to touch the electroscope with my negatively charged PVC tube, what will happen? The electrons here will jump onto the electroscope. And here you go. What happens here, or the electroscope will be completely negatively charged. Negative and negative repel one another. So the rod will be, or the little stick here, will be repelled from the rest of the electroscope. Now, when I touch with the positively charged glass rod, the electrons which are in excess on this electroscope will go toward the glass rod, effectively making this electroscope neutral again, or at least more neutral, depending on how much electrons can get away. And it will close again. Now, we also have a phenomenon called electrostatic induction. This is a little bit different. I do not touch the electroscope with my tube. I close with the tube or a rod, and we should remember that those repelling or attracting forces, they do not need to touch each other. They're kind of field forces. They are field forces. So negative and negative repel one another. So when I get close enough, the electrons here on top will move away. Depending on how close, it will be a different amount. So when I get closer, first let's finish here. So the top here will be positively charged, and the bottom will be negatively charged. So the stick opens because it is repelled by the rest of the electroscope. When I get closer, like here, you see more electrons will go down. This bottom will be more negatively charged, and the stick will open wider. Now, when I connect the electroscope to the ground, it's grounded, like here, those electrons, they can go down here, but they go that because they're pushed away by this one, but still there's now a more preferable way, which is towards Earth. And as we see, the electrons happily go this way now. So the electroscope here stays neutral. And as we look at it, the complete part of the electroscope looks, together with the tube, is neutral. We have as much positively charged positive ions, and negatively charged electrons. And they form one stable or neutral medium. But it's all fake, because when I move the grounding, it's still the same. But next, I remove the rod. And when I remove the rod, electrons will push each other away as much as possible. So they try to occupy they try to push each other so much away as they can. Which happens that leaves the electroscope positively charged, because it lost electrons here, in this piece. So the stick opens, and we have, well, a positively charged object. Through electrostatic induction, we have given a permanent charge to an object without touching it. We gave the electroscope a positive charge. Example. Well, let's look at a few examples here. We've got here water, and water in fact is a dipole. Water is a dipole and has opposite charges on each side. the whole of a water molecule, it's neutral. But the hydrogen atoms are a little bit down here, and they're more positively charged, so we get here a positive side and a negative side on water. What happens when we approach with a negative charged PVC tube? Well, here are the water molecules coming down, and they're at random. But the positive side is attracted by the negative, and the negative is repelled by the negative charged tube. So they turn around like this. Now the positive side is slightly closer to the negative tube compared to the negative side. So here are attractive forces and here are repellent forces. But the attractive forces, because of that they are closer, will win. So the molecules will slightly move towards the negative charged tube, causing the water flow to go like this. The flow of water. Well, we have a neutral metallic sphere in this example. Here's the neutral metallic sphere close to a positive charged object. What happens? Well, the electrons will all move to the left side because they're attracted to the positive charged object. The electrons will move to there and leave the right side positively charged because the electrons have moved to here. Those electrons are closer to the positive object than the positive ions. So the electrons have moved here, and this force is stronger. This attraction force is stronger than this repellent force, so the sphere will move towards the positive charge object. One final example. Remember the little paper pieces from the first movie? How can we attract neutral, non-conductive paper strips with a charged object? Well, we have the charged object here, but the paper is neutral. And there's no free-flowing electrons, like in a metallic sphere on the previous slide. Well, the electrons which orbit their nucleus will have an orbit which is slightly out of center here, and the electrons will orbit a little bit more on this side, causing in effect to have the atom become a dipole. In this atom, the orbit of the electron is warped toward a positive charge, creating a dipole. In the paper, what happens? All of the atoms will form little dipoles, with the minus on this side closer than the positive side of the dipole of the atom, so causing an attractive force. The atoms form dipoles and are attracted by the positive charge. Good. Let's look at conductors and insulators. What's a conductor? A conductor has electrons in the outer layer and they're loosely bound. They move around freely. So what we have, for example, here we have a nucleus with 26 protons, like iron. We got the electrons in their orbits, but one or two of those electrons are not loosely bound, are not really bound. They're more loose. So in fact we have a positive ion here and a free jumping around electron. And we have more atoms in a piece of iron. So we have a piece of iron here with the ions and the free jumping around electrons. And they really jump around. They go from one to another and back, and they do that all the time. When we have, for example, here the same iron, but this time I have a big electrical negatively charged object here. Well, negative repels negative, so those electrons will move away from that side, in fact causing an electric flow in this piece of iron, where the electrons are pushed away by the other electrons. Then we have insulators. What are that? That are atoms, for example this one here, with 14 protons in the center, and the electrons are really tightly bound. They have no free, loosely bound electrons, and they cannot move around freely. So no electrical current in this one. A few examples: conductors and insulators. Conductors iron, copper, which are metals, and metals are most time conductors, are all conductors, and insulators are like rubber or plastics. A few ceramics, also insulators. A special exception or special plastic is conductive plastic. Polyacetylene is a plastic which can conduct electricity. They exist. And for example, nerve cells, don't forget the human body. The nerve cell is a good conductor. Now, the whole human body is, but the nerve cell is a specialist in that. Well, now we've studied those forces, but we need a formula for that. And that we'll see in the next few movies. But first, we need to make a little sidestep towards vectors, to be sure you understand that one.